I thank the organizers and the conveners of this session for giving me this opportunity to give this talk. And so I will first give a general introduction to this idea of neutrino oscillations, and then I will talk about neutrino oscillations at INO in particular. In one question which people, scientists and philosophers have thought about probably from past 2 or 3,000 years is what is matter made of, and of course there were various speculations, but a substantial and quantitative picture started emerging, I would say, in the last 300 years. First, people realized that if you go to the smallest part of any given matter, you will encounter a molecule, but later advances in chemistry showed that all molecules are made up of combination of a rather limited set of atoms, that is only about 92 or so. But about 100 years ago, there was a even more drastic simplification of this picture, which said that all matter is made up only of 3 fundamental particles: positively charged proton, negatively charged electron, and a neutral particle with no charge, which is neutron. And everything we see in the universe is made up of these 3 particles in various different combinations. However, there is one aspect which is troubling. In beta decay, that is a neutron decaying into a proton, the energy is not conserved. If we apply conservation of energy, energy of electron should be mass of neutron minus mass of proton, but when you do the experiment and measure the energy of the electron, you get that continuous distribution varying from 0 to a maximum value of neutron mass minus proton mass. So, does it mean that we give up on energy conservation? Some people actually were willing to do so, but Pauli is a great believer in energy conservation, and he said, I will use this, what he called a desperate remedy of proposing that there is actually a third particle also which is produced, and this third particle is taking away the missing energy, and that is the proposal of neutrino. That is when people first started talking about neutrinos, and to account for the data, this third particle, it should have 0 charge, so that conservation of electric charge holds, and also conservation of energy implies that the mass of this third particle should be much smaller than electron mass, which is already the lightest known particle. And a fellow physicist called Fermi named this particle neutrino, meaning Fermi is Italian, and so in Italian neutrino means little neutral one, to distinguish it from neutron, which is the massive neutral particle. And this neutrino is the first of the various exotic particles which people have discovered over the last 80 years or so, and I am sure all of you have heard of this great excitement which occurred about 5 years ago when the Higgs boson was discovered. So, Higgs boson is, as of now, the last entry in this list of exotic particles, but we hope that there are many more entries to come. This same Fermi, he constructed a theory of beta decay based on Pauli's proposal, and this theory agreed with the data so well that people just accepted that there is a neutrino, even though nobody ever saw a neutrino. And in fact, people made an estimate about the chance of actually observing a neutrino in the lab and concluded that it's not possible at all. The reason is, you take a neutrino, let's say of energy 1 MeV and an electron of energy 1 MeV, and both of them enter a detector, and the probability that neutrino will interact with the detector is 10 power 18 times smaller than the probability that electron will interact with your detector. So if you say that electron will interact in a microsecond, then the probability you have to wait some 10 power 12 seconds for the neutrino to interact, that is like a million years. So chance of observing a neutrino interaction seems very, very small, practically undetectable. However, in fact, this is a famous cartoon which illustrates the situation, that just because you proposed a particle but say that it's undetectable doesn't mean that it exists. But mind you, in the case of neutrinos, we have very strong reason to believe that it exists, because the Fermi theory, which is based on neutrinos, explains data extremely well. But all this was before World War II, and after World War II, one had nuclear reactors, and nuclear reactors were putting out something like 10 power 12 to 10 power 14 neutrinos per second. So if you wait for a couple of years, then there is a chance that you can actually observe some neutrino interactions. So based on that hope, two experiments were conducted. One looked for conversion of a proton into neutron, and the other looked for conversion of neutron into proton induced by neutrino. The proton to neutron conversion experiment, it saw a signal. They could see the neutrons being produced in their detector, and in fact the person who conducted the experiment was awarded Nobel Prize in 95. But the other experiment, neutron to proton conversion, did not see a signal. There were no argon atoms in the detector. And of course, we understand this by saying that it is antineutrinos which convert protons to neutrons, and neutrinos convert neutrons to protons, and reactors produce antineutrinos. That is why the first experiment saw a signal and the second experiment did not see a signal. Obviously, the person who did the second experiment, he was very upset, and this is this gentleman called Ray Davis, and he started looking for a source of neutrinos so that he can also see a signal. And the source he found is the sun. There are nuclear reactions, nuclear fusion taking place in the sun, and in the process of nuclear fusion, enormous number of neutrinos are being emitted. In fact, even though the sun is so far away, something like 100 trillion neutrinos are passing through each of us every second. So there are enough neutrinos to detect, and Davis indeed succeeded in detecting these solar neutrinos. And here I want you to sort of think of the achievement. He had a detector which is like 1,000 tons, which contained something like 10 power 36 atoms. Out of 10 power 36 atoms, he managed to pull out the 10 argon atoms from the detector. People talk about searching for a needle in haystack, but this is like needle in a billion haystacks. However, there is a problem. Problem is that the value measured by Davis is only 1/3 of what is expected, because we have a reasonably good understanding of how the sun is producing energy. Then question is, why is that? Is something happening to the neutrinos as they are coming from sun to earth? And this is the first hint we have that neutrinos are not just showpieces just there to conserve energy, they actually have much more interesting properties. Well, that is one of the surprises we had, but nature had many more surprises, and in particular people studying cosmic rays in the 1930s, they found some very puzzling features, and they finally explained those features by saying that there is another exotic particle called a muon. This muon is a charged particle and it is some kind of heavier cousin of electron. Electron has unit charge and it has mass of something called half an MeV, whereas muon also has unit charge and it has a mass of about 100 MeV. And here I should mention that Dr. Homi Bhabha, who set up the Indian atomic program, he played a key role in figuring out this puzzle, and in fact I believe he was considered for a Nobel Prize, but for some reason he was not awarded one. And scientists, after discovering the muon, started studying its properties in a systematic manner and found some more puzzling features, and in order to explain those puzzling features they had to propose that there is actually another neutrino which is different from the neutrino that was proposed by Pauli, and so they started naming things systematically. Pauli's neutrino is called electron neutrino, and this neutrino which is coming in muon decay is called muon neutrino. And the proposal was made sometime in 1950 or so, and 10 years later in an experiment in the US this muon neutrino was explicitly seen, and this experiment also was awarded a Nobel Prize in 1988. Now let us talk about this muon neutrinos. The experiment done in the US produced muon neutrinos quote artificially, they produced them in a lab, but people doing the Kolar Goldfield experiment, they realized that these muon neutrinos are also produced naturally in the atmosphere, because you have cosmic rays coming and hitting an atom in the atmosphere, and that interaction, there are large number of steps, but eventually that interaction produces this muon neutrino, and you can detect those muon neutrinos in the Kolar experiment. And as Amol already mentioned, in 1965 the Kolar Goldfield experiment detected these muon neutrinos in atmosphere for the first time. Now let us come to this business of neutrino oscillations. Soon after the discovery, just months after the discovery of second neutrino, 3 Japanese physicists, they proposed this, you can say, really wild idea in which an electron neutrino can spontaneously turn into a muon neutrino. In all the previous transformations we talked about, there is a decay or an interaction. Here there is no such thing. I have an electron neutrino coming like this and spontaneously it becomes a muon neutrino. So this is something completely different, and but it's a possibility, and that is what these Japanese physicists proposed. And for this oscillation to occur, two things should happen. The two neutrinos should mix in some way. I mean, one can define this mixing in a mathematically precise way, but I don't have time to do that now. And another important thing is that the two neutrinos should be massive, very small mass, mind you, maybe million times smaller than electron mass, but non-zero mass, and also unequal masses. That's the requirement. And the probability of oscillation depends on the four quantities that I listed there. And after this proposal, people started speculating whether the deficit of solar neutrinos that I mentioned earlier, whether it is due to neutrino oscillations. So this is the first hint we have of neutrino oscillations. Now let us talk about a different problem which is called atmospheric neutrino problem, and that begins with this famous statement by Richard Feynman. I am sure all of you have heard of Feynman, his lectures are very famous. Fermi once made a statement that yesterday's discovery is today's calibration, to which Feynman added, well, yesterday's discovery will become tomorrow's nuisance. But here this atmospheric neutrino problem is a case where what is meant to be nuisance actually gave rise to a discovery, and that discovery came through this means. Professor Kajita talked about it and he got a Nobel Prize for it. There are neutrinos coming from all around the earth. Those coming from above travel few kilometers, those traveling from below travel thousands of kilometers, and those coming from above do not oscillate, but those going from below, they oscillate. So there is a atmospheric neutrino deficit, and this is the data for which Professor Kajita got the Nobel Prize, and this is our present knowledge of neutrinos. There is a larger mass square difference and smaller mass square difference, and what we try to do in INO is to study that larger mass square difference in detail. And why exactly do we need to construct INO? It is the only atmospheric neutrino detector with a magnetic field, and this magnetic field enables us to study matter and antimatter separately, and that provides a much better detail of the whole neutrino physics and atmospheric neutrino problem compared to all the other detectors. So, and over the past 15 years, there is a large enthusiastic group of young researchers and PhD students who are working on INO, and we all hope that this project will start soon. Thank you.